So before now, we have gone through stress strain curve in tensile mode. So now we will be focusing on stress strain curve in compression mode. So in general, this test is also done on universal tensile testing machine. Place the sample between the platens which are connected with the clamps. Then we apply force in compression mode. So initially we have elastic deformation. The dimensions of this sample will decrease elastically. Means in this region, if we remove the force, the material will regain its original dimensions. After that, plastic deformation starts. So initially we have in plastic deformation bulging of the sample, and if we continue to pressing, so it leads to flattening of the sample. So now we will see a video animation about this test. So this is the sample which is placed between the platens. Now we are in plastic zone. There is bulging starting. So if we compare stress strain curve in compression and extension mode, so in both we have elastic and then plastic regions. The plastic region in compressive mode is simple. So there are only two major deformations. The first one is bulging and then flattening. While in extension mode, we have yielding, strain hardening, necking, and then fracture. Another difference between both is that in most of the material, the strain in compression is much lesser as compared to strain in extension mode. There are mainly two types of loads, static load and dynamic load. And we perform two types of testing, static testing and dynamic testing, in order to measure stress versus strain. So in static test, the load is applied slowly and the precise rate of loading is not of interest because it doesn't affect the behavior of specimen. For example, if someone is sitting on a bench, so the load he or she is applying on that bench is a static load, and in order to check its capacity whether it will fail or not, we need to perform a static test. In dynamic tests, the load is applied rapidly and sometimes in a cyclic manner. Since the nature of a dynamic load affects the properties of material, the rate of loading must also be measured. So here is an example of cyclic loading. And due to this cyclic loading, there will be a strain in the object which will be removed again with loading. There will be strain and so on. So here is the stress strain curve. This stress strain curve shows the material behavior within elastic range. So in first there is loading. So we have a strain. We remove the load. So during unloading step, material regains its initial position. We increase the load, loading again, unloading comes to original position, loading, unloading, increase the loading. So during loading step, we have a strain and then we remove it, comes to original position. So this was example of elastic loading, unloading within elastic region. So if we cross the elastic limit, what happens? So here is an example. We were at point O, initial zero loading step. We applied loading. There is deformation. Here is elastic limit, then yield point. And if we go beyond to that, so we will have a permanent deformation. During unloading, there will be some recovery. We call this elastic recovery, but we will have a residual or plastic or permanent strain. So in next cycle, we will start it from here. We will have some deformation. We come back, some recovery, some permanent deformation, and so on. So the plastic deformation will increase with each cycle. So in cyclic loading, the material fails much below than their ultimate tensile strength. Such failure is called fatigue failure. So when the material is subjected to a cyclic load, there is a crack initiation, propagation, and then failure. So we will see this video, 7 to 8 minute video. This gives us an overview of how the material fails under cyclic load, what is fatigue failure, what is ascent curve. So let's start it.
Components which are subjected to loading which varies with time can fail at stresses well below the material's ultimate strength. This is known as fatigue failure, and it accounts for the vast majority of mechanical engineering failures worldwide. The bolts in an office chair, the crank arm on your bicycle, and pressurized oil pipelines are just a few examples of components which are subjected to time-varying loads and may be at risk of fatigue failure. Fatigue failure occurs due to the formation and propagation of cracks. It is a three-stage process. The first stage is crack formation. This usually occurs at free surfaces and at stress concentrations. In stage 2, the crack grows in size. And in stage 3, after the crack has grown to a critical size, fracture occurs. So how can we figure out whether a component is likely to fail due to fatigue? One common approach is to run fatigue tests by subjecting a component or test piece to a large number of constant amplitude stress cycles and counting the number of cycles until it fractures. If we repeat this test a large number of times with different applied stress ranges, we can plot the results on a graph with the number of cycles to failure n on the horizontal axis and the applied stress range s on the vertical axis. Because the number of cycles to failure can be very large, a log scale is usually used for the horizontal axis. By fitting a curve to the data points, we obtain what is known as an SN curve. The SN curve allows you to calculate the number of cycles until a component is likely to fail for a given stress range. For example, if we have a stress range of 100 MPa or 15 KSI, this SN curve tells us that the number of cycles to failure is 500,000. If we know that our component is subjected to 1 cycle per minute, we could predict that our component will fail due to fatigue after approximately 1 year. Fortunately, we don't have to perform these time-consuming fatigue tests ourselves. SN curves for many different materials are already published in different engineering codes. For some materials, and in particular for ferrous materials, it is important to note that the SN curve at a very large number of cycles becomes a horizontal line. This is known as the endurance limit. Theoretically, the component could be cycled at stress ranges below this level forever, and it will never fail due to fatigue. This makes the endurance limit an important fatigue design parameter. It is common to differentiate between high cycle and low cycle fatigue. High cycle fatigue occurs when the applied cyclical stresses are low, and failure occurs after a very large number of cycles, typically more than 10,000 cycles. Because the stresses are low, we are only dealing with elastic deformation. Low cycle fatigue involves higher applied cyclical stresses, and failure occurs after fewer cycles. Because the stresses involved are above the material's yield stress, both elastic and plastic deformation occur. In these cases, a strain-based approach, using for example the Coffin-Manson relation, is usually preferred to the SN curve approach. If we return to the data from our fatigue tests, we can see that there is a large amount of variability in the data. This is typical for fatigue tests, even when identical test pieces are used. If we use a best fit SN curve, as we have done here, there is a significant possibility that our component will fail at a much smaller number of cycles than the curve predicts. This test piece, for example, failed at a much lower number of cycles than predicted by our SN curve. For this reason, SN curves published in engineering codes are normally shifted downwards by a certain number of standard deviations to give a reduced probability of failure. Here, by shifting the mean curve down on the vertical axis by 2 standard deviations, we have reduced the probability of failure from 50 to 1%. Fatigue tests are usually run for the constant amplitude fully reversing cycles you can see here. The same stress magnitude is applied in tension and in compression. Let's define a few terms. The stress range is defined as the difference between the maximum and minimum stresses. The stress amplitude is defined as half of the stress range. The mean stress is the average of the maximum and minimum stresses. In this case, the mean stress is 0, but this is only one very specific type of loading. In some cases, we might have a mean stress which is not equal to 0, as shown here. This mean stress will have an effect on the fatigue life. A tensile mean stress will typically result in a shorter fatigue life. One way to account for a tensile mean stress is to use SN curves derived for specific values of mean stress. But these are often not available, or would be time-consuming to obtain. Another approach is to use the Goodman diagram, which adjusts the endurance limit to account for a mean stress. Let's see how it works. On a Goodman diagram, the mean stress is shown on the horizontal axis, and the stress amplitude is shown on the vertical axis. A straight line is drawn between the endurance limit, at a mean stress of 0, and the material ultimate tensile strength, at a stress amplitude of 0. If our cyclic loading conditions are located below the Goodman line, our component will be safe from fatigue failure. There are a few different variations of this diagram, as you can see here. This approach can only be used to determine whether a component will have an infinite life. It doesn't allow us to calculate a fatigue life. In many real-world cases, the applied loading is likely to be far more complex than what we have considered so far. We can use techniques like the rainflow counting method to simplify a complex stress spectrum into a number of simpler, constant amplitude cycles. Miner's rule allows us to account for the cumulative damage caused by each of these different constant amplitude stress ranges. It calculates the damage fraction D as the sum of the fatigue damage contributions for each stress range. The individual contributions are calculated by dividing the number of cycles by the number of cycles to failure for that stress range. The damage contributions from all stress ranges are then summed. If the total sum damage fraction is greater than 1, fatigue failure is considered to have occurred. In this example, the damage fraction D sums to 0.94. This is less than 1, and so fatigue failure has not occurred. If the structure we are assessing contains an existing crack, the SN approach is not suitable for determining the fatigue life. If the dimensions of the crack are known, we can instead determine the fatigue life using a linear elastic fracture mechanics approach. This involves calculating a critical crack size, which would result in fracture, and using a crack growth law to calculate the time required for the crack to grow to this critical size. But that's enough about fatigue.
Equations that characterize the physical properties of a material of a system are called constitutive equations. It is possible to find the applied stress knowing the strains and vice versa. First definition is of Poisson's ratio. If you look at this rod, when we apply an extensional load, so there is an extension and at the same time there is a lateral strain as well. Material become thin in this direction. So if we take negative ratio of lateral strain and this tensile strain, so it's called Poisson's ratio. So this will be Poisson's ratio xz. So here are the value of Poisson's ratio of some materials. For example, for stainless steel, its value is 0.3, for aluminium 0.35. So what does it mean? It means that when we stretch this body in this direction, so if there will be 1 millimeter strain in tensile direction, there will be 0.3 millimeter strain in this direction. For example, aluminium's Poisson's ratio is 0.35, copper's Poisson's ratio is 0.37, and rubber's Poisson's ratio is 0.5. So ultimately, you can imagine for rubber, when we stretch a rubber, the change in this direction is higher. For example, 1 millimeter strain in this direction, 0.5 millimeter, which is quite significant in lateral direction. So stiffer is the material, lesser will be its Poisson's ratio. So next is Hooke's law. When strains are small, most of the materials are linear elastic, and the ratio of their stress and strain, it will be equal to a constant. So this constant we called E, or the tensile modulus in case of tensile loading. And in case of shear loading, the ratio between shear stress and shear strain, it will be equal to G, which is a constant, we say rigidity modulus. The relation between tensile modulus and rigidity modulus, these both are in fact dependent on the material, is given here. So shear modulus is equal to Young's modulus divided by 2 into 1 plus Poisson's ratio. So now we will be talking about relation between stress and strain if the loading is uniaxial, biaxial, and triaxial. So what does it mean, uniaxial stress? For example, we have a rod, we are stretching it. So the stress is only in one direction. It will be given as sigma xx equal to modulus into strain. There is no force or stress is applied in this direction or in z direction. So when we will stretch it, there will be a deformation in this direction and a thinning or strain in y and z direction. Means its diameter will decrease. So by application of uniaxial stress, we will have a strain in all three directions. So strain in, as we have seen in last slide, so strain in this direction and in this direction, they are related uh, using an equation. They are linked by this Poisson's ratio. So if we know strain in x direction, we can calculate strain in y direction using this Poisson's ratio. So Eyy, that will be equal to negative of Poisson's ratio into Exx. So this is the value of epsilon xx, and similarly epsilon c, it will be equal to Poisson's ratio into epsilon x. So in short, when we apply unidirectional stress, there will be strains in all three directions. So it's quite possible that these strains are very like have low value as compared to this strain, and we neglect it in order to simplify the equations. But in engineering, we need to consider it. So if we have biaxial stress, for example, stress is applied in x and y direction and stress in z direction is 0. So due to this sigma xx, there will be strain in three directions, and due to this sigma yy, there will be strain in three directions. So cumulative strain will be equal to, for example, epsilon xxx will be equal to sum of strains caused by this plus this. Similarly, epsilon yy will be equal to sum of strains caused by sigma xxx plus sigma y, and EZZ will be equal to sum of strain caused by this plus this. And if we talk about triaxial stress, means stress is applied in three directions. So all three components of stress will have their impact, means in the form of strain, and we will have to add impact of all three in all directions to get cumulative strain. For example, epsilon xx will be equal to strain caused by sigma x, strain caused by sigma yy, and strain caused by sigma zz. And same will do for the remaining. So if we talk only about linear stresses, there will be three components of stress in x, in y, and in z direction. And if it's combination of linear and torsional stress, so in that case, total stress will have six component, one, two, three due to linear, and this these three tau yz, tau zx, and tau xy due to shear or torsional stress. And similarly, they will have six cumulative components in the form of strain, which are given here. And a relation between stress and strain, it can be written like here in matrices form. So stress is directly proportional to strain, or when we link it, there will be a constant can write it, denote it with S, with Q, with R. So mainly it's rigidity or constant of proportionality, and it will have like its components. So if stress is applied only in one direction, means unit axial stress, we have talked about it that it will have three components of strain. So the constants, components of this constant, we will have like 36 components, and they can be calculated using this stress and strain relation. This is the matrix if triaxial stress is applied. So three components of stress, three components of strain, and this is rigidity matrix. So for all the components of this matrix, we will calculate it using the Hooke's law. What it says that the constant will be equal to stress divided by strain. So the first component will be equal to this stress divided by this strain. The second component will be equal to this stress divided by this strain. The third component will be equal to this stress divided by this strain. And same is for the other components. So for isotropic strains, these equations, the value of these constants becomes very simple. So when we apply load, there are several possibilities for the constitutive equation, for you can say Hooke's law, which is stress equal to constant into strain. First thing is only mechanical load is applied. So equation will be very simple. If we are heating the object in addition to mechanical loading, the equation will become a little complicated. The stress which is being applied, it will be a function of temperature and is equal to C constant. This constant or rigidity of material is also a function of temperature. It changes with temperature, and this uh, epsilon or strain, it will also depend on temperature. How? If we are stretching the body and we are cooling it at the same time, so total strain will be lesser as compared to mechanical strain alone. So due to mechanical force, it will stretch, and due to thermal contraction, due to cooling, its dimensions will decrease. So total strain will be lesser, or it can be written as epsilon minus CTE delta T, where CTE coefficient of is coefficient of thermal expansion. So especially for polymers, if we are talking about uh, a thermoset polymer to which we are heating and at the same time cross linking is occurring, so there will be an effect of cooling thermal, there will be an effect of shrinkage, and then an effect of mechanical loading. So such constitutive equation is called thermochemical and elastic equation, or this approach is called thermochemical and elastic approach. The stress will be equal to rigidity, epsilon minus or plus thermal or minus or plus chemical. So if this thermal is increasing the deformation due to mechanical loading, it will be positive, and if it is decreasing it, then it will be negative. Similarly, this is chemical shrinkage, so it will be reduction in dimension. So if we are in tensile mode, means we are increasing the length and shrinkage is decreasing, so its sign will be negative, and in compression mode, it will become positive because it will be supporting the compression. Similarly, due to humidity, the materials expand as well. So if we want to consider the effect of humidity, then this approach or constitutive equation is known as thermochemical and hygroelastic approach. And we will be considering effect of temperature, effect of shrinkage, and effect of humidity as well. So all these equations were written while considering that material behavior is elastic. So for polymers in general, the material behavior is viscoelastic, means time dependent. We will be learning about it later on. So all these equations, they become function of time, because viscoelastic means the material behavior is function of time. It changes depending upon time in addition to other parameters. So these equations, thermochemical elastic, thermochemical hygroelastic, all these becomes a function of time when we talk about this. Factor of safety is an important term in mechanics of material. So it tells us about how we are safe in terms of materials strength. So for example, we have a material with a given or actual strength. So the required or surface strength, it must be lesser than the material's actual strength. And ratio of these is equal to factor of safety. For example, if we have a material with actual strength of like 120 megapascal, and the required strength is for a surface, the required strength is 100, so factor of safety will be equal to 1.2. It means our required strength is 20% lesser than the actual strength. So factor of safety, it must be greater than 1 while designing a mechanical structure. Then another definition is allowable stress or working stress. So it's calculated using factor of safety, and it's equal to yield strength divided by factor of safety. And similarly, allowable or permissible load means how much load will be safer. We will calculate again using this allowable stress or yield strength and a factor of safety. So allowable load will be equal to allowable stress divided by unit area. So if we have a bar, we applied a load on it, P, it will have some deformation. So work done required to deform this bar is equal to strain energy, and is defined as the energy absorbed by the bar during the loading process. So how can we calculate it if we have a curve or graph between load and extension? So area under that curve, it will be equal to the strain energy. Or strain energy is denoted by U equal to work done, and it will be equal to integration of this load and displacement curve. P1 is the load, delta 1 d delta 1 is the small displacement, and if we integrate it from 0 to given displacement, so it will give us the work done. Or you can say it's the area under the P and displacement. So if we again remind our last slides, so when we apply a load, there is elastic limit, then we enter into plastic region, and when we come back here, there is some elastic recovery, and this is plastic deformation. So this area it will be called elastic strain energy, and this area it will be called inelastic strain energy. So if we consider only linear elastic region, or we say that material behavior is linear elastic, so the curve between load and displacement, it will be a straight line. And if we want to calculate energy, so we need to calculate area under this curve or the work done. So this becomes a right angle triangle, and area of right angle triangle can be calculated by multiplying height base divided by 2. So this work done will be equal to P into means load into displacement or extension divided by 2. So as we know that strain is equal to stress over modulus, or strain can be further defined as extension over original length, stress force per unit area, modulus is E. So delta extension, it will be equal to force into length, or here force is denoted by P, which is load, divided by E into area. So this will be the value of this delta in terms of load applied, initial length, modulus, and cross-sectional area. So if we put this value of delta into this, so we will have the value of strain energy equal to load square L divided by 2EA, or it can be written in the form of extension. So it means if we know the load applied, initial length of a bar, its modulus, its cross-sectional area, so we will be able to calculate its strain energy. And similarly, if we know the extension in the material only, in addition to its initial length, its modulus, its area, we will be able to calculate its strain energy again. There is another term which is known as strain energy density. It's defined as the strain energy per unit volume. So we denote it with small u, and it's equal to strain energy per unit area, per unit volume. So its equation, it becomes this in terms of load and this in terms of displacement. So we took the value of u from the last slide, and we divided it by a volume, which will be equal to area multiplied by capital R. We can write it also in terms of stress and strain. The equations are given here. We need to only replace P over A with stress and change or extension by length with strain. So these are our equations. So last definition for today is modulus of resilience is strain energy density of a material when it's stressed to a proportional limit. So this value, which is strain energy density, if it is taken at the proportional limit, so this value is called modulus of resilience. So it will be equal to stress square over 2e, but we will take this value of stress at proportional limit, so small subscript, and we will add subscript r with this energy density, which shows that this energy density is calculated, is called modulus of resilience.